This is a short video that starts section 2.3.2 in Stein's number theory book about how to compute a to the m, but then reduce it mod n. So there's a lot going on in this section, and in this first video that we're going to do, we're really going to focus on this algorithm 2.3.11, which is a way to write a given number in binary. Maybe you've heard of binary before. So maybe what's the overview of this whole section though? What we'd like to do is, as it says, compute very large powers of some integer a and reduce them mod n. And a naive approach, of course, is to just multiply it all out and reduce it mod n by repeatedly, again, just multiplying. But that involves some huge numbers. It gets very large. And so, as it says, it's also, from like kind of an algorithmic point of view, it's pretty inefficient. So it's horribly inefficient because you're going to do m-1 multiplications. And of course, if you're thinking about using this stuff for cryptography purposes, that m that you're going to use, this power, is going to be incredibly large, maybe even hundreds of digits. So that many multiplications is pretty taxing for a computer to do even. So what we're going to do is, again, the overview is what's a better way to compute a very large power of a and reduce it mod n. And we'll see that it really comes down to writing the exponent in binary, and then after that we'll see that once we have that binary expansion of m, the exponent, we're going to think about writing a to the m now as just a product of expressions a to the power of 2 for various I. And we'll see that that gives maybe a simpler way again, to compute the actual large power a to the m via some of these smaller powers. So what we're going to focus on is this part. We need to be able to write an exponent, or in our case, just any integer m, in binary. And so maybe you have some ways to do that. Maybe you've seen that before. So the way I'm going to tell you to do it, again, just follow this algorithm down here. Maybe before I even get into that, what is binary? You might think of it as base 2. And so how can I express a number only using 0 and 1? And so what are we used to? We're used to base 10, and maybe let me give you an idea over on the side here. If I'm thinking about base 10, the point is I'm thinking about any number can be expressed as a sum of powers of 10. So maybe something like, 23, I just picked that randomly, that's equal to what? So the first power of 10 I would get 2 times 10 to the first, in that case, plus 3 times 10 to the 0, right? That's how you read 23. 2 is in the tens place, and 3 is in the ones place. I hope that you see that there. So what we want to do is we want to take 23, say. I'm not going to do 23, but we'll take 23, and the idea is, how do I write that as a sum? Instead of powers of 10, I'm going to write it as powers of 2. And so that hopefully explains this notation down here. And our only coefficients that we're allowed, maybe notice in my example up here in base 10, the coefficients I was allowed to use. If we're in base 10, I've got numbers like 0 through 9. So you see that I use 2 and I use 3. So I'm only allowed to use those digits 0 through 9. But if I'm going to write something in binary, the coefficients, which we're going to denote by epsilon I, they only get to be 0 or 1. So how do we turn a number, again, into binary? So here's kind of the algorithm, and what we're going to do is try to follow it. So as it says, we're always going to start our sum from I equals 0, and r is just however many powers of 2 that you need. So we'll set I equal to 0, just like it says to do in the sum here. Now, if your m is already 0, terminate, you're done. So the binary expansion of 0 is just 0. Otherwise, though, what you're going to do is you're going to look at, if m is odd, then the coefficient, this first coefficient, epsilon 0, right, since we started with I equal to 0, it's just going to be 1. And otherwise, the coefficient, epsilon 0, is going to be 0. Now what we do is we increment I. What that means is, all right, now we're going to go I equals 1. And so we're going to look at the next term in this summation here. And what we'll do with our m as well, the m that we have, we're going to divide it by 2. And what we'll do is, if m's divisible by 2, in other words, if m's already even, there's nothing to worry about there. But if m is odd, then what we'll do is when we divide by 2, we'll take the floor of m over 2. And so what that means is I want the greatest integer that's less than or equal to m over 2. And now we just repeat the process. We go back to step 2, and we ask ourselves, okay, if our new m is 0, we're done. Whereas otherwise, if the new m we get is odd, then the next coefficient is 1 on that next power of 2. Or otherwise, the next coefficient on that power of 2 is 0. So let's do an actual example that tries to highlight some of these. So let's try m equals 12, say. And I want to write 12 in binary. So what would it look like? And what I'm thinking about again is just like, well, what are the powers of 2 that I get to add together to make 12 if I'm only allowed to use 0 and 1 as the coefficients on those powers of 2? And again, just to emphasize, that's what this says here. So what are we going to do? Well, I look at step 2. Maybe I should set I equal to 0. So that should be step 1. I equals 0. And now I'm going to look, is the m I got odd? I look at 12. Nope. So otherwise, epsilon 0 in this case, remember I is 0, is 0. So step 3, epsilon naught is 0. Now what I'll do, just because it says 2 in the same step, I'm going to change I from 0 to 1. So I is 1 now. Now I go to step 4, which is to divide by m by 2 basically, and just take the greatest integer less than or equal to m over 2, just in case it was odd. We're good though, because for step 4, m is going to be 6. And now it says go back to step 2. So we look at our m. Is it 0? No. So we go to step 3. Is it odd? No. Is it even? Yes. So what we have then, back to step 3, is that now the next epsilon, epsilon 1, is equal to 0 again. Now what we'll do is we'll increment I one more time. We'll go to step 4, which was to take 6, our m, and divide it by 2, and set that to our new m. So m is 3 now. And we just keep going back. So now what we're going to look at is that an even or odd number? And finally we're to a point where, okay, my m is 3, so it's odd. So now what I've got is epsilon 2 should be 1. Now I'm going to set I equal to 3 for the next step. Also now, when I go, why'd I put a 5 there? I should have put a 3. I'm just kind of repeating back and forth to step 3. When I go to step 4 again, when I go to divide by 2, I'm going to take 3 divided by 2. That's 1.5. So the floor of 1.5, the greatest integer less than or equal to 1.5, would be 1. So my new m is 1. So for m is equal to 1 now. And in that case, we'll go back to step 3. Since m is 1, that tells me that epsilon, I is 3, remember? Epsilon 3 is equal to 1 as well. And now I would set I equal to 4, but when I go to divide my m, oops, that wasn't what I wanted to do. When I go to divide this m, when I go to step 4, the floor of 1 over 2, the floor of a half, is 0. So my new m is 0. Finally, I'm to a point where it says, when I go to step 2, if m is 0, terminate, right? Don't go to step 3. So that means we're done. So what do we got? What we just found is all of our coefficients. So 12, it should be equal to, I'll write this out. Remember the form we had was like epsilon 0 times 2 to the 0, plus epsilon 1 times 2 to the 1, plus epsilon 2 times 2 to the 2, plus epsilon 3, right? 3 was the last I that we got something for, times 2 to the third. And so how you would look at that then is we'll plug in our numbers, 0 times 2 to the 0. I'm going to leave it because I really just care about the coefficient. And we said epsilon 1 is 0 times 2 to the 1. By the way, where am I getting this stuff from? I'm keeping track of this information here. Now I'm going to plug those in for each of these on my powers of 2. Plus 1 times 2 to the 3, 2 to the second, and then plus 1 times 2 to the third. So what do I care about then? What is 12 in binary? In binary, what we're going to do is we're going to kind of read this backwards, just like you would for when you talked about in base 10, right? Like with 23, since the 2 is in the tens place, I put the highest power of 10 first. I'll put the highest power of 2 first, the coefficient there first. So it should be, I should read this as 1, 1, 0, 0. So 1, 1, 0, 0 would be the binary expansion of 12. Again, there's different algorithms for how to write a number in binary. If you've got a quicker one, go for it, use it. This is just a convenient one. And Sage can do this stuff also, so let's maybe take a look at that. So if I wanted to write a number in binary here, all I've got to do is say the number, and then dot, and then the function that I need is just str, so I mean string. We're going to think about this number 12 as a string, and I want to do it base 2, so I just do parentheses 2. And when I hit enter, it's going to think for a second because it's just freshly running. And we get that 1100 should be the binary expansion of 12. If we go back to take a look at the book, they do another example too, where they do the binary expansion of 100. And so they check it first with Sage, and it should be 1100100. So remember how you should read these things, another way to look at it, just so everybody's clear. We're saying that this is the coefficient on 2 to the 0. This is the coefficient on 2 to the 1. This 1 is on 2 squared. This 0 is on 2 cubed. This is on 2 to the 4th, and I think you see what I'm doing. And finally, this is on 2 to the 6th. So that would be the binary expansion again. I just care about the coefficients that are on those powers of 2. And also, they've just written that out exactly right here as well. So you see that those coefficients that show up in the binary expansion are just on these very large or successively larger powers of 2, and it adds up to 100.